Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, we're joined by Dr. Feba Pulikkottil. Feba earned her Master's in Organic Chemistry from Christ University in Bangalore before pursuing her PhD in the Indian Institute of Science, Education and Research, IISER. During that time, she worked on transition metal catalysis and silicon chemistry under the guidance of Dr. Ramesh Rasapan. Currently, she's a postdoc in the group of Professor Kevin Lamb at the University of Greenwich, where she works on electrochemistry and fluid chemistry. And from there, I'll hand it over to you, Feba. Thanks a lot for coming on today to share your chemistry.
Hello everyone. Thank you for the kind introduction. Today, I'm excited to share insights into my work on the electrochemical synthesis of carbamoyl fluorides from oxamic acids. So what are electrochemical reactions? Before diving into the specifics, let's first understand what electrochemical reactions are. Simply put, they involve the transfer of electrons between molecules or atoms, converting chemical energy into electrical energy or vice versa. Advantages and applications of electrochemical reactions. One of the key benefits of electrochemical reactions is their environmental friendliness. They provide a versatile alternative to traditional redox reagents, which are often toxic and expensive. Additionally, electrochemistry enables transformations that are otherwise inaccessible using conventional chemical methods. It is valued for its simplicity, cost-effectiveness, and speed while being a safe and sustainable approach. From an application standpoint, electrochemical reactions are widely utilized in various industries, including batteries, electroplating, fuel cells, and metal corrosion protection. Solving synthetic chemistry challenges with electroorganic chemistry. A great example of how electroorganic chemistry can resolve synthetic chemistry problems comes from the work of Phil Barron in 2014. During the total synthesis of the bis-carbazole natural product dexamycin, he faced difficulties in dimerizing the monomeric precursor using traditional chemical oxidants. However, by applying a specific electrochemical potential, the desired dimerization was achieved at a reproducible and scalable yield of 28%. While dexamycin was synthesized on a milligram scale, synthetic organic electrochemistry is regularly employed on industrial scales, producing compounds like acetone, acetylene dicarboxylic acid, 2-amino-methylpyridine, and arabinose in quantities of thousands of metric tons annually. One of the largest electrochemical processes is the oxidation of 4-tertiary butyl toluene, a key step in synthesizing the perfume ingredient lismeril, which is produced at over 10,000 tons per year. Focusing on electrochemical reactions. Among various electrochemical reactions that are available, my focus today is electrochemical fluorination. Fluorinated compounds are highly valued due to the unique properties they impart to molecules. This has led to a continuous search for innovative fluorination methodologies. However, carbamoyl fluorides remain unexplored, likely due to the scarcity of efficient synthetic methodologies. Existing methods rely on expensive, hazardous, and often explosive reagents while yielding poor to moderate results. The significance of carbamoyl fluorides. If successfully synthesized, carbamoyl fluorides can serve as precursors to important functional groups such as amides, urea, thiocarbamates, and carbamates. These carbamoyl fluoride-derived functional groups are integral to bioactive molecules, including drugs like ritonavir, which acts as a HIV protease inhibitor, irinotecan is used in the treatment of colon cancer, fencerin is used in Alzheimer's treatment, darunavir acts as HIV protease inhibitor, lenifenib and sorafenib acts as anti-cancer agents, and finally, rivastigmine and physostigmine act as cholinesterase inhibitors. Developing a new electrochemical methodology. Recognizing the need for better synthetic approach, we sought to electrochemically synthesize carbamoyl fluorides from oxamic acids. Some of the previous literature examples are shown here. Traditional methods involve reagents such as trifluoromethoxysilver, carbon dioxide DAS systems, or trifluoromethyl trifluoromethane sulfonate, all of which require excessive amounts of silver salts or toxic, volatile, and explosive reagents. Other methods using bromodifluoroacetates provide only moderate yields. Due to the lack of efficient methodologies, the properties and applications of carbamoyl fluorides have remained largely unexplored. We then decided to optimize the reaction methodology to bring about the best conditions for the successful preparation of these carbamoyl fluorides. On the basis of our previous experience with anodic oxidation of oxamic acids, we started our investigations with electrolysis of our standard substrate in DCM using 2 equivalent of the mild and less corrosive fluorinating agent triethylamine trishydrofluoride at a current density of 8.9 mA per centimeter square. We used carbon graphite as the anode as a result of its low cost and ability to perform multiple electron transfers. For the cathode, we chose platinum foil electrode because of its low hydrogen overpotential property. To our delight, the desired carbamoyl fluoride was obtained with a yield of 95% under these conditions. The reaction parameters were then further investigated as can be seen in rest entries of the table. As expected, the electrode material proved to be an important factor, entries 1 to 4 for the cathode. While the use of carbon graphite as cathode, which has a higher hydrogen overpotential, did not affect the yield of the reaction, entry 2. The use of less noble metals with low hydrogen overpotential, such as nickel and stainless steel, not only performed as well as platinum cathode, but also gave very clean transformations without significant byproducts. Entries 3 and 4. Therefore, cheap and readily available stainless steel was chosen as the cathodic material. Entries 5 to 6. While testing for anode material, carbon graphite was found to be superior to platinum. Entries 7 and 8. In terms of solvents, DCM was shown to be better than acetonitrile. Entries 5 and 7. With regard to the nature of fluoride sources, entries 9 to 13, tetrabutyl ammonium hydrogen fluoride was found to be efficient as triethylamine trishydrofluoride in achieving the desired fluorination. Entry 11. Interestingly, the use of tetramethyl ammonium fluoride, a better nucleophilic fluoride donor, did not result in any improvement. Entry 12 and 13. Finally, the ideal amount of triethylamine trishydrofluoride was found to be 1.5 equivalent. Entries 14 to 16. The effect of current density and the cause of the reaction was also investigated. A lower current density led to similar excellent yields, entry 17, but surprisingly required a longer electrolysis time. On the other hand, a higher current density resulted in lower yields, entry 18. We then explore the substrate scope to assess the robustness of our methodology. Various functional groups including alkenes, alkynes, esters, sulfones and nitriles were well tolerated, leading to good to excellent yields. However, aniline derivatives resulted in lower yields unless an electron-donating methoxy group was present, which significantly improved the reactivity, yielding 80%. The method also proved compatible with both aliphatic and aromatic halides, spirocompounds, and late-stage modifications of complex molecules, though some drug derivatives exhibited modest yields. Given the challenges associated with large-scale synthesis of carbamoyl fluorides, we explored transferring our method to a flow electrochemistry setup. By optimizing the flow parameters, we achieved an impressive throughput of 60 gram per hour per liter, a six-fold improvement over batch processing. Further scale-up on a 1 gram scale in batch confirmed that the reaction remained efficient, yielding 98% of the pure carbamoyl fluoride. Based on cyclic voltammetric studies, we propose a plausible mechanism. Through CV, we identified that a standard substrate exhibited a chemically non-reversible oxidation at 1.54 voltage. So the mechanism goes like this. The first step is oxidation of oxamic acid 1 to formation of an unstable carboxyl radical 2, which then undergoes decarboxylation, leading to the generation of an acyl radical 3. This acyl radical then undergoes further second electron transfer to form highly electrophilic cationic intermediate 4. Finally, the fluoride anion is trapped to form the desired carbamoyl fluoride. In summary, we have developed a novel, mild, practical, and scalable electrochemical synthesis of carbamoyl fluorides using triethylamine tris hydrofluoride as an easily handled reagent. The reaction is highly efficient, does not require strictly anhydrous or degassed conditions, and tolerates a wide range of functional groups. Additionally, we have demonstrated its scalability both in batch and flow electrochemistry, paving the way for future industrial applications.
And now Feba is going to give us a short demonstration of her chemistry in action.
my postdoc advisor, Professor Kevin Lamb, Dr. Jeremy and John for their invaluable contribution to the project, colleagues from Lamb Lab, University of Greenwich, finally, Matthew and Synthesis Workshop team for this wonderful opportunity. And this is my beautiful team members. Thank you all for watching, and I look forward to any questions you may have. Thank you.
Thank you for joining us for this Research Spotlight episode, and thank you very much to Feba for sharing your work with us. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on social media to stay up to date, and see you next time.